Welcome to the talk, Advanced Data Modeling. My name is Shtub, and I'm head of training at ScyllaDB. So this talk is happening right now. It's live, and I'm using two screens. I'm checking the chat window on the other screen as I'm talking. So feel free to say hello, maybe where you're coming from. And as I'm talking, I'll try to make it as interactive as possible. Feel free to ask questions. Let me know if I'm going too fast or too slow in the chat window. Okay, great. I see people from Paris, from the UK, from the US, from all over. So thanks again for joining. Okay, so this is me. I'm a software engineer. I've been with ScyllaDB for almost 7 years, and I'm based in Israel. The things that I would like to cover today are an introduction to ScyllaDB and to NoSQL in general. Then, pretty much depending on you, I can talk a bit about the architecture of NoSQL databases and specifically ScyllaDB and some basic data modeling. I'm going to check in with you, and if I see that you already know that part, then I'll skip it. I'll talk about the partition key and the importance of how we choose it, collections, counters, user-defined types, and time to live, which are more advanced data modeling topics, large partitions and collections, hot partitions, cardinality, and tombstones. And finally, if we have enough time, also I'll talk about the monitoring stack and what happens when we have issues, performance or otherwise, and how do we diagnose them and fix them. I'm also going to be using some hands-on labs. These hands-on labs are going to be available to you on ScyllaDB University. So let me put the link in the chat window. It's university.scylladb.com. And I'll also send you an email after this talk, probably tomorrow, with the slide deck and the links to the labs. Okay, so you don't have to worry about, I don't know, taking photos of the slides or anything like that. Okay, so ScyllaDB University, I mentioned, is our training resource center. It's a website that has lots of recorded videos, hands-on labs, quizzes, lots of material covering pretty much everything that you're going to be seeing today in depth. And it's available to you. To use it, all you have to do is create a user, you register a free user, and then you can start taking lessons. The material there is available whenever you want. So it's self-paced. You can take courses whenever you like. And then we also have docs.scylladb.com. That's our documentation website where you can find more in-depth procedures, material, and yeah, it just goes more in-depth into different flags you can use with commands and other stuff. Okay, so let me start with a few words about ScyllaDB. ScyllaDB is a distributed NoSQL database built for very high performance, which means a high throughput and low latency. It's used by some big companies from different industries. And I'm guessing that you'll know some of these companies here, Expedia, I don't know, Zillow, Palo Alto Networks, Tesla are also a customer. They're not here. But we have some big companies using ScyllaDB. Yeah, please mute yourself. Thank you. Okay. Yes, thanks for that note. Let me move that thing. I hope it's better now. Is my sound okay? Can people hear me? Okay. Yeah. Let me know if there's any issue. Okay, so some of the attributes of ScyllaDB. I mentioned it's a distributed database. It's built with high availability in mind. And what does high availability mean? High availability means that the database can serve requests even if there are some failures, and these can be network failures, hardware failures. the database has built-in redundancy, and it holds multiple copies of each piece of data. Okay, so data is replicated, and this is done automatically. And I'll talk about how that works under the hood in just a bit. The system is also highly scalable, and that means that it's very easy to add or remove nodes as the system is running. Okay, so this happens without any downtime, and it's quite easy to add or remove nodes. The system automatically redistributes the data across the new nodes, or if we remove nodes, it can redistribute the data to the existing nodes. A use case of this might be, say, we're using ScyllaDB for an e-commerce application, say website, and we know that Black Friday is coming up and our traffic is going to spike. So before Black Friday, we can add more nodes to our cluster. The database will be able to serve more requests. And after Black Friday, maybe we want to decommission those nodes and go back to the previous number of nodes that we had. Okay, I mentioned performance. So I mentioned high throughput as well. So when I say high throughput, I mean we're looking at use cases that have hundreds of thousands and even millions of operations per second. Okay, so that's a very high throughput. And it also works with a very low latency. And when I say low latency, I mean single millisecond queries. Okay, so we have P99, which means like the average, well, it's not average, it's like 99% of the queries perform within single millisecond times, which is very fast. So if you have a real-time use case, if you have large data, big data, then ScyllaDB is probably a good option for you. Low maintenance, so the system has auto-tuning abilities, and it does most things without any intervention needed from the user. And I didn't mention it, but ScyllaDB is a drop-in replacement for Apache Cassandra and Amazon DynamoDB. Okay, so there are dozens of databases out there for different use cases. Some big ones are Apache Cassandra, DynamoDB. You probably heard about Redis, about Mongo. And if you have an application that's currently using Cassandra or DynamoDB, you can use your application as it is and just replace the underlying database to ScyllaDB, and you'll get different benefits. I don't really want to go into the details, but this is just one example of a customer that switched from Apache Cassandra. They had 40 Cassandra nodes. They replaced that with 4 ScyllaDB nodes, and they got a solution that was much faster, 11 times faster, and also way cheaper. Okay, so don't take my word for it. You can find the exact details on our website and different migration paths from different databases. In this slide, I'm not going to show you the demo. It's a bit out of scope, but you can see there's a link here to a GitHub project where you can actually run a 3-node ScyllaDB cluster with just a few clicks, and you'll get to see how it runs more than 1 million operations per second at very low latencies. So this here we can see is below 1 millisecond. Okay, so before I dive into data modeling, maybe we can do a quick question just to make sure that you're with me. So the question is, what's your current NoSQL status? If you can quickly answer in the chat window. Is this the first time you're hearing about NoSQL databases? Maybe you heard about NoSQL, but you've never used it before. Or maybe you're already using a NoSQL database. If you can take just a few seconds to answer in the chat window, I'll know that I'm not talking to myself. So what's your NoSQL status? Okay, so thanks everyone for the answers. I see it's quite varied just from taking a quick look I see the audience here is a mix. Some people are already using NoSQL databases, some haven't heard about it, and some heard but haven't used it. Okay. And I see some MongoDB users, some Cosmos DB, and others. Okay, so the title of this talk is Advanced Data Modeling, but of course, if I want to go into advanced data modeling, I want to first make sure we're on the same page regarding architecture and basic data modeling. Otherwise, I'm pretty much going to lose you. So let me start with some more basic concepts, and let me know in the chat window if you already know these concepts or if it's too slow for you, and then I can skip some, okay? So I kept saying things like cluster and nodes, and I never really explained what that means. So basically, a node is the ScyllaDB software that runs on a server. That's a node. And since ScyllaDB is a distributed database, we have a number of nodes that work together to serve requests, and that's called a cluster. Okay, now I'm talking about ScyllaDB here, but the concepts that I'm talking about right now are the same, pretty much exactly the same for Apache Cassandra, for DynamoDB, and for other wide column databases. Okay, so in this example, we see a 5-node cluster. We have 5 machines, and these machines are located in different places, and they're all working together to serve requests, okay? I mentioned high availability. So in ScyllaDB, data is replicated, and that means that the database holds multiple copies of each data, okay? This is something that happens automatically. The user only has to set the replication factor, and after defining the replication factor, data is automatically replicated to different nodes. Okay, now you can imagine that if we have multiple copies of each piece of data, and those copies are stored on different nodes, even if a node becomes unavailable, or there is whatever, network failure, or maybe an earthquake, then other nodes can still serve requests, okay? So replication factor is the number of nodes where data are replicated. And this setting is determined once when we define the key space, okay? You can see an example here. Create key space with a key space name, with a replication, and here the replication factor is 3. Okay, a key space is a container of tables. So all the tables that are defined within this key space are going to inherit this replication factor of 3. And that means that all the data within those tables will be replicated 3 times. Okay, and I'm going to show you an example of how that happens. Okay, so here we have again our 5-node cluster, and say we define the replication factor to be 3, then each piece of data, say this orange cube is a piece of data, will be written to 3 different nodes. In this case, node 1, node 2, and node 3. A different piece of data might be written to other 3 nodes, and so on. Okay? How does this happen under the hood? Okay, so the way that it works under the hood, if you're not speaking, please mute yourself. There's an echo. Thank you, Sazia. Okay, so how does this happen under the hood? I didn't mention it, but in ScyllaDB, all nodes are created equal. We don't have the concept of primary node, secondary node, or any other name you want to call it. All nodes are equal, and all nodes can serve requests. When a client, say, wants to write a piece of data, say we have this table with 3 columns, PetShip ID, time, and heart rate, and we want to write one of these rows into the database. What the database does is it takes something called the partition key, which is defined as 1 or more columns, and it uses a consistent hash function to know which nodes are responsible for that specific piece of data. Okay, so let me repeat that. This is important. Whenever we define a table, we have to define a partition key, which is one or more columns. Okay, in this example, the partition key is the pet ship ID, so this piece of data. And when we read or write data, our query has to include the partition key. The database takes the partition key, performs a hash function on that partition key, and by doing that, it knows exactly where this, in which node, and also within each node where that data exists, okay? And I'm showing you how this happens under the hood, but as a user, all you have to do is define the partition key when you define the table and provide the data when you read or write from the database. Okay, another way to look at it is here we can see the key space, which is, like I mentioned, a high-level container for tables. We can have one or more tables in each key space. And by the way, an application can have more than one key space, but it might also have just one key space, depending on your needs. And within each table, we have different settings like the partition key, which I just showed you. And the way it works is that sometimes ScyllaDB and Apache Cassandra are called key value databases. So we have the partition key, which is one key. We have an optional other key, which is called the clustering key. And then we have the values, okay? And I'll show another diagram to better explain it. Okay, so I talked about the replication factor. I see there's a question about the partition key. I'm going to talk a bit more about it, and if I don't answer your question, then please let me know and I'll answer it. So the consistency level, abbreviated as CL, is the number of nodes that must acknowledge a read or a write request. Okay, different possible values for the consistency level can be 1, can be quorum, can be all. There are different values. And the consistency level is determined per query, okay? So I might have a read query that has a lower consistency requirement, then I can define it as 1. And that means that only one of the replica nodes has to respond to the query for that query to be considered successful. On the other hand, say I have a write query that's very important, and I want to have a higher consistency for that specific query, I can define the consistency level for that query to be, say, all, and then all 3 replica nodes, instead, in case I'm using a replication factor of 3, will have to respond to that query for it to be considered successful. Okay, so it's easy to see that there is a trade-off between availability and consistency, right? And also costs, of course, because if we have more nodes, more hardware, more storage, then the cost is going to go up, but we're also going to have a higher availability and higher consistency. The trade-off between availability and consistency is that if we define a consistency level that's higher, in case we have one node go down, say we define a consistency level of all, if one of the replica nodes goes down, then the query will fail. However, if we define the consistency level of quorum, then only 2 out of 3 nodes need to acknowledge the request. And then even if one node goes down, the data would still be available. Okay, so there is a trade-off, and this is something you have to consider when you create your data model. Okay, so I talked about ScyllaDB being a distributed database running multiple nodes. It also can use multiple data centers. And in this example, we see a bigger cluster with how many? 5, 8, so I guess 13 nodes. And these nodes are distributed across 3 data centers in different geographical locations. Does anyone have an idea why we would want to use multiple data centers? There are a number of reasons. Maybe you can guess in the chat window. Okay, so why would we want to use more than one data center for our cluster? Okay, so some of the answers are reliability, latency, backups, outage, availability. Okay, so you're all correct. There are a number of reasons, and let me say a few words about that. So closer to the client, that's also a good point. So when we use multiple data centers, well, there are a number of reasons we might want to do that. One is high availability. ScyllaDB is topology aware, and that means that it knows which data centers it's using, and it also knows about racks within the data center. Okay, so that provides an additional layer of availability. And even in the very unusual case that an entire data center goes down, the other data centers would still be able to serve requests. And when the data center goes back up, the other data centers would stream the data to the data center that was unavailable. I know this might sound extreme, and it's true, it doesn't happen a lot. However, we did have one use case that I recall where one of our customers or users was using multiple data centers, and there was a fire in a big data center in Europe. A lot of websites went down, but this customer was able to continue using their application, and their clients didn't suffer any outage because other data centers were still available. Okay, so that's high availability. Another reason that people here wrote is latency. So because of simple physics, it takes time for data to travel, say, from the United States to Asia, and it would make more sense to serve users from the United States from a data center that's geographically closer to them. And of course, the same for other locations. Another reason that I don't see anyone wrote in the chat window is for compliance reasons. Okay, so some jurisdictions might have a requirement to keep the data of users from that country or geographical area within that country, say. And by using multiple data centers, we can define, for example, that the users of our application from Europe would have all their data only in the Europe data center. Okay, so it wouldn't be replicated elsewhere. So lots of options, but that should give you an idea. Let's skip this question. I have a lot of material to cover. Okay, so let's talk a bit more about the partition key. It's quite important when we think about our data model. Okay, so I talked about the partition key, and the partition key is defined as one or more columns in our table. And the database, well, it's mandatory. Every table has to have a partition key, and the database knows how to partition the data according to the partition key. Okay, so here we can see in the green rectangle is the partition key, and each one of these is a partition, and the partition points to the other data. In this case, it's time and heart rate, okay? When we define the partition key, all the queries must provide the partition key. Otherwise, the database would not know where our data exists, and it would have to do a full table scan. So it would have to scan all of the nodes to find the data. It would have no idea where the data exists. So that's the partition key. The second part of the primary key is called the clustering key. The clustering key determines for a given partition what would be the order of the data within that partition. Okay, so if we define a partition key as the pet chip ID in this case, and we define the time to be the clustering key, then for all values with the same pet chip ID, these values would be stored according to the time. Okay, so that's what you can see here. And when we define the clustering key, it makes queries that use the time much more efficient. Okay, so what would happen under the hood? ScyllaDB would take the partition key. It would know exactly where that partition exists on which nodes. And because the data is ordered according to the time, if we want to look for a specific time or even a time range, we can do that very, very efficiently. Okay, and as a side note, clustering key is called ordering key in some databases like DynamoDB. In my opinion, it's a better name, ordering key. That makes more sense. But we sort of inherited clustering key from Apache Cassandra. Okay, let's talk about data modeling in NoSQL databases and compare that to relational databases, just because I'm assuming that many of you come from a relational background. So the typical process for data modeling with relational databases is that we first of all think about our data, we create an entity diagram, we think about the relationships between our data, and from that we derive the model, schema, and finally we think about our application and we can create queries. In NoSQL, it's similar, but also there's a big difference. And the big difference is that instead of thinking about the application at the very end of the process, we have to think about the application at the very beginning together with the data. Okay, so when we create the data model, we have to think about which queries we're going to be using, what is the required consistency level for each query, and how often are we going to be using that query. Okay, so we think about it at the very beginning, and from the application and the data, we derive our schema. Okay, and unlike what you see here in this slide, it's not a one-time process, so it's actually iterative, and we derive the schema. Usually we test it, we might run it in production, and then go back to the beginning and make some modifications. Okay, so this is an important slide. If you're coming from a relational background, keep this in mind. Okay, so there are some things that are easy to get wrong. It can seem easy, but things like hotspots, imbalances, large partitions, and tombstones, which are more advanced, and I'll try to talk about these as well. Before I do that, let me switch to a lab. So I am going to show you the high availability lab. Okay, maybe I'll maximize this. How does the font size look? Can you read the terminal? Is it too big or too small? It's okay. Great. Okay, so before I maximize this screen, I just want to show you that we're using a platform here that runs from within the browser. Okay, so this is a platform that runs virtual machines within your browser, and that means that you don't have to worry about prerequisites or your operating system or whatever. You just need an internet connection and a browser, and then you can run these labs. And like I said, I'm going to be sharing the links to those labs with you together with the slides by email probably tomorrow. Okay, so the lab that I'm going to quickly show you is called the High Availability Lab, and it demonstrates some of the things that we talked about. When you run the lab yourself, you're going to see the explanations here. I'm going to skip them right now. And what I'm going to do is I'm going to run this command here. Okay, so I clicked run, it copied these commands. And basically what it did is it ran 3 ScyllaDB nodes. You can see the command here. It's using Docker run with a node name, specifying the ScyllaDB version. And we're providing these two flags, which basically tell ScyllaDB that we're running a testing environment. So it's not production, and we can relax some of the performance requirements. Okay, so I started a 3-node cluster. I didn't mention it, but when we run in production, the recommendation is to use at least 3 nodes, and we have customers running clusters with hundreds of nodes. Okay, so between 3 to many, many nodes. Okay, great. Now, I started my 3-node cluster and I want to make sure it's up and running. So I'm going to use a command called node tool status. And what I did is I simply executed on one of the nodes. There are 3 nodes, node X, node Y, and node Z. And I selected one of the nodes, node X, and I ran node tool status, which basically checks to see if my cluster is up and running and what's the status. Now, when you run this at home, the status might be joining or unavailable yet. It might take, I don't know, up to a minute for the cluster to get up and running. Great, so I see that my status is UN, which is up and running, and I'm ready to start running requests. I can check the logs to see what's up, but I'm going to skip that. And I can connect to my database with a CQL shell. Okay, so the CQL shell is an interactive command line interface that we can use to perform queries to interact with the database. In a real-world application, you're typically not going to use the CQL shell. It's usually done for testing purposes, for debugging, and so on. Typically, for a real-world application, you're going to be using drivers. And in ScyllaDB University, there's an entire course focused on drivers in different languages. But we're just playing around with a small cluster here, and we're going to be using the CQL shell. Great. So we have our 3-node cluster up and running. We're connected to that cluster with a CQL shell. And now we can start interacting with the database. The first thing that I'm going to do is I'm going to create a key space. I'm going to run this command here, create key space, just like you saw in the slides, call it my key space, and define the replication factor to be 3. Okay, and if you remember, replication factor of 3 means that there are going to be 3 copies of each piece of data. Now, using this key space, I'm going to define a table. And if you remember, a key space is a container of tables. So now if I define a table, say users, that table is defined within the key space. So it inherits the replication factor from the key space. Okay, so I defined a table called users. It has 3 columns. It's very straightforward, like you would expect. Column name and type. So user ID, type integer. First name is a string, last name. And I define the primary key to be user ID. Okay, now if you remember, the primary key has 2 parts, or can have 2 parts, and that's the partition key and the clustering key. Does everyone remember what the partition key and the clustering key are? You can write in the chat window, partition key and clustering key. Do I need to repeat that, or are we on the same page? If anyone doesn't know or wants me to repeat, please say so in the chat window. Okay, so I'll repeat that. So in ScyllaDB, and again, I'm saying ScyllaDB, but it's also for other databases, we have for each table something called the primary key. The primary key has 2 parts. The first part is the partition key, which is mandatory. We have to define a partition key, which is 1 or more columns. Okay, that's the partition key. And the database knows how to partition or to place the data within the cluster according to the partition key. Okay, so partition key is mandatory. It can be 1 or more columns. In this case, it's 1 column, user ID. And in this case, let's look at this example, the table users. For each query that we read or write data to the database, we're going to have to provide the partition key. If we don't provide the partition key, we're going to get an error. Okay, maybe I'll show you how that happens in just a bit. So that's the first part, the partition key. The second part of the primary key is called the clustering key. sometimes also called ordering key in other databases. And that part is not mandatory. Okay, so here it's not defined. In this table, there's no clustering key, but later on, hopefully, if we have enough time, we're going to see examples of tables that use the clustering key as well. When we define a clustering key, the clustering key, so it can be 0 or more columns. And if we have more than one value for a given partition, so say we have, for the same user ID, we have two different users, okay? It doesn't really make sense in this example, but imagine we do. Then for the same user ID, which is the partition key, we would have different values of first name and last name, and they would be ordered according to the clustering key that I defined, okay? Okay, let's move forward. So now that I defined my table, I'm going to insert some data. So insert into table name users, I provide the column names, and I provide the values, okay? Very simple and straightforward. And now that I have this data in my database, I can run a select query, and I can read the data, and it's there just like I would expect. Okay, now if you remember, in this key space, we define the replication factor to be 3, and that means that there are 3 copies of each one of the rows that we saw here. Okay, the 2 important concepts that I talked about were replication factor, which is the number of copies of data we're going to have, and the second one was the consistency level, okay? Now, in these queries, I wrote data and I read data, and I didn't define the consistency level. The consistency level in SQL SH, in the shell, by default is 1, okay? Now, let's see what happens when we use different consistency levels, okay? So I'm going to show you an example. We're going to connect to our cluster again. And now, instead of using a consistency level of 1, we change the consistency level to be quorum. Okay, and with the consistency level set to quorum, a quorum is a majority of the replica nodes. So in our case, we have 3 replica nodes. A quorum would be 2 out of those 3 nodes. Okay, so I insert data into my database, just inserting another user. And just as I would expect, this operation would succeed as all nodes are up. Now, I'm going to skip forward a bit just because I want to show you more stuff. But when you run this lab on your own, you're going to simulate a situation where some nodes are unavailable. And you're going to do that by simply, because we're using Docker, it's easy. We're simply gonna shut down those nodes using Docker. And when we do that, we're going to see what happens when we perform queries at different consistency levels. Okay, so you can imagine that if we set consistency level to all, and not all 3 replica nodes are up and running, then the query would fail. Okay, you're going to have a chance to run this on your own. I do want to move forward to some other topics. Okay, so let me see if there are questions. So there's a question about clustering key. Is it the same as indexes in relational databases? So it's not exactly the same. We have a different definition for indexing in NoSQL databases. That's a more advanced topic. Maybe if we have time, I can touch on that. But we have something called secondary indexes, which allows us to denormalize data, and that's different from clustering key. And there's an entire lesson on ScyllaDB University just about indexing. So if I don't cover that, you can also look there. Is there a way to add UUID automatically similar to PostgreSQL built-in procedure? There might be a way to do that through the drivers. Okay, so when I use the CQL shell, as far as I know, there's no way to do that. But I believe that the drivers can do that, but I'm not sure, so you can check. Another question is, why are there multiple copies of the same table? From Carlos, I'm not sure I understand, but maybe I'll sort of say that we don't have copies of the same table, but we have copies of the data within the table. Okay, so we store, potentially, we don't have to, but typically we would store more than one copy of each row in the table, and we would store it on different nodes. And the reason we do that is because we want to achieve high availability, so that even if one node goes down, there's a hardware failure, there's a network failure, or whatever, we can still serve requests. Okay, in your application, you might have tables that require a higher availability setting, okay? Or you might have tables that don't require any redundancy there, okay? So then you can define a replication factor of 1, and then that table will have only one copy, okay? Maybe that table doesn't require high availability. Okay, so you can play around with that, and again, that goes together with thinking about your application when you create your data model. Okay. So there's a question about the recording, and I believe the recording will be available together with the slides and the labs. So we'll share an email with that information. And there's another question. Clustering key, is it similar to foreign key? So it is similar, but it's not exactly the same. Where can we see the nodes present, or is it defaultly taken as 5? Okay, so the nodes, there's a completely separate component called the monitoring stack, which is based on an open source project called Prometheus. And there you can see what's happening in your cluster. And when you create a cluster, you can define how many nodes you want to use, and that's based on your requirements, okay? I didn't mention it, but I sort of skipped that part. You can run ScyllaDB either on-prem, on your own, or on any cloud that you choose, but you can also run it, we can run it for you basically as a service. So we have a database as a service offering, and then you don't have to worry about, I don't know, things like security hardening, upgrades, you get support, we take care of the sizing, and you can just focus on your application. Okay, so there's a question about failover strategy in the event of losing nodes. So we do have a calculator that shows you, so again, there's a trade-off here. If we have more nodes, the availability would be higher, but there might be, well, there are definitely going to be cost implications, but there might also be latency implications. So there's a trade-off between the number of nodes and cost and latency and availability. And we have a calculator available that helps you determine the best sizing according to the availability that's required in your application. Okay, so let me try to cover a few more topics, going back to the slides. Yeah, and this slide says, please install the monitoring stack. Okay, this is how the monitoring stack looks like. And distributed databases, distributed systems in general, they're complex entities, and it's hard to understand what's going on. Whenever users ask us to help them with problems, the first thing we tell them is show us your monitoring stack, because it's really hard to know what's happening without the monitoring stack. The monitoring stack has different dashboards. You can see what's happening per data center, per node, even per shard within a node. You can see latencies, performance, troubleshoot different problems. So yeah, if you're planning on running ScyllaDB in production, by all means, install the monitoring stack and use it. Okay, that's really important. Okay, maybe a few more words about advanced topics. I won't really go into the details, but for each one of these topics, I want to sort of mention it just so you know that it exists and you can learn more about it if you feel the need to. Another thing that I don't want to forget is our community forum. Okay, so we have a lively forum where you can ask questions. If you come up with questions after the talk today, something that you didn't get an answer for, or you remembered after the talk, you can ask it in the community forum. And our engineers hang out there. I also check it. So you can just ask there. And you can also ask about your use case, say how you're using ScyllaDB or how you're interested, and say hello there. Let me put the link here in the chat window. And you're welcome to say hi. Okay, so collections. We have 3 types of collections: sets, lists, maps, and user-defined types, which are more advanced. There are caveats and pros and cons for each one. In some cases, it makes sense to use collections depending on your application and on the data model. Okay. In other cases, it doesn't. There are some examples here. I'm gonna just run through it for lack of time. You can see the exact difference between maps and sets and lists in the slides and on ScyllaDB University. And another useful type is counters. Counters, just like it sounds, is a special type of column that can be defined in a table. Most of you are probably familiar with what a counter does. You can increment or decrement it. It's very simple. But the main important thing about the counter is that it provides the decrement and increment in one atomic operation. So we guarantee that it will be done in a consistent fashion. Okay, and that's very important. And there are also some caveats for things you can do or not do with columns that are of type counter. Okay, user-defined types are more advanced. In this example, we have a type that's called geo, and it has an altitude, a latitude, and a longitude. And then we can define a table that has this data type. Again, it's more advanced, but keep in mind that it exists. And if you need to use it, you can read more about it. Yeah, I know I'm like rushing fast through different topics, but we're almost out of time and I want to just touch on each one of them. Time to live. So time to live is very useful when we're talking about big data. For some use cases, specifically IoT use cases, that's what comes to mind, but I'm sure there are others. Some data becomes obsolete. Thanks for letting me know. Can you see the TTL slide now? Yes, okay. Sorry about that. Thank you. So TTL is time to live. And I was saying that in some use cases, data automatically becomes obsolete after a while, and that could be after a year or after a week and so on. I don't know, a classic IoT example that we use is that we have an application with different pets, and each pet has a collar, and that collar has different sensors, and the sensor measure different parameters for the pet, say a dog, and they send that data to the database, say every second. So for example, we might measure the heart rate of the dog every second, or the temperature of the dog, and so on. And in that application, we can define that data that's older than, say, 1 week is no longer relevant and we can erase it. Okay, so if we don't do that and we measure data every second, then after a while, our data is going to grow very much. And TTL allows us to keep a check on that and automatically delete data that is no longer relevant. Okay, there are different ways to define it. Here it's defined in seconds, and you can see exactly how to do it on your own. I won't go into that. But basically, you define the TTL once, and then all the data with the TTL automatically gets deleted after the time to live. Okay, large partitions and collections. Not sure we have enough time for that. But maybe I will say a few words about the importance of choosing a partition key. Let's see if I have a slide on that. Okay, let's do it without a slide. I don't know where it is. So let's talk about hot partitions and large partitions. I mentioned that, let me go back to the slide where we do this. So I mentioned, and I hope you can see the architecture slide now. Okay, so I mentioned that ScyllaDB knows where to place the data according to the partition key. So when we create the data model, it's very important to choose a partition key that makes sense. And what do I mean by makes sense? What we want to achieve is an equal distribution of the data, okay? And we also want to avoid hot partitions. So there are two topics here, large partitions and hot partitions. Since we have 5 nodes, we want, like I said, to have an equal distribution of data. If we have a partition key that, say, let me just give you an example. So say we're modeling people in the United States, okay? So we have a table of people in the United States, and one of the columns is state, which state that person lives in. If we choose as a partition key the state, then that would not be very good data modeling, because some of our states are, some of the states in the United States are big. They have a lot of people like California or Texas, whereas others have much less people, say, I don't know, Delaware or other smaller states. Then our data will not be evenly distributed, and we would have some nodes with a lot of data and some nodes with very little data, and we would not be making very good use of our resources. Okay, so another reason not to choose state is because there are only 50 states. Okay, we want to try to aim for values with high cardinality, like PetShip ID, where there are a lot of possible values and not just 50 values. So that was an example of a large partition. The partition of, say, California or Texas would be large, and the partitions of smaller states would be small. Another example, which is, or another topic that is similar but not exactly the same, is hot partitions. So maybe say that we use states, but in an imaginary United States, all the states have the same number of people, so we don't have to worry about large partitions. All the partitions are of the same size. But in our application, for some reason, we query people from California more than other states. Okay, so if our database, our application, sorry, significantly has more queries for people from California, then the California partition would become a hot partition, because it would be very loaded, and that would create a hot partition and some performance issues. Okay, so we want to avoid hot partitions and large partitions, and for that we need to choose a partition key wisely. There is another lab here that I'm not going to show you. It's the basic data modeling lab. Let me see, it's this one. Okay, it also runs in Instruct, and I'll share the link to that as well. And you can play around in that lab with different partition keys, clustering keys, what happens when we read or write data. and you can run that later on. And with that, we're pretty much out of time. Maybe let's see if there is another question or two, we can answer that. Yeah, let me just write my email here, so you can also feel free to reach out if you have questions later on. And I mentioned as resources, ScyllaDB University, the community forum, and our documentation website. I'll be sharing the slides and the links with you probably tomorrow. Stored procedure, that's a very advanced question. I'm pretty sure we can, but yeah, that's a good question. I would have to check. I think we can, but I know that it's an advanced feature. I'm not sure if it's defined as sort of like a beta feature or if it's something that's already available in production. But we can definitely look into that. It's probably written in documentation, and you can also ask that in the forum and we can check. Okay, so there is a question about relational databases and clustering solutions for high availability. And basically, I read the question is, when should we use ScyllaDB? I'm going to post an answer just because it's a long answer and we're almost out of time. So I'm going to post this here. And this answer from the community forum pretty much covers when you would want to use ScyllaDB. I'll say it in just a few words. If you're having millions of operations per second, if you're running terabytes or petabytes of data, and if you require high availability for real-time workloads. Okay, if your focus is analytical workloads, maybe look elsewhere. If you're running mixed workloads, then you can work with ScyllaDB. But if you're just working analytical workloads, then maybe don't use ScyllaDB, but check out that answer. It goes more in depth. And with that, we're out of time. Thanks, everyone. I hope you learned something. And yeah, stay in touch. Thank you very much.
Gary.